Okay, everybody. Well, today, as promised, we'll actually get into it, start from the very beginning, instead of having high-level overviews. Right, so we're going to talk about one qubit today. Right, so in computing, right, we have a concept of a bit, which is 0 or 1. Okay? And actually, that's a logical concept, right? When we come to talk about algorithms and circuits and computer science, it's a logical concept, a bit. But it's physically represented in some sort of machine or physical device. And how is a physical bit stored? Well, I'm not an expert on this either, but like maybe in the olden days where there were wires, it would either have like a low voltage on the wire or like a high voltage. Okay, that was like the physical implementation, and then you just said logically this is a 1 or a 0. Okay. Or maybe on a hard drive, like some kind of region is either like magnetized or demagnetized, and then you just call these two states 0 and 1. And yeah, then you get started. Now, again, I don't really know, but presumably if you have like some electricity like coursing through a wire or something, that's like a million electrons, maybe. Million physical particles all representing this one logical bit. And of course, these days we're really into like miniaturization, like let's try to make things as small as possible. So you might ask, can we get some physical, can we get a logical bit using like one physical particle, like one electron or one photon? And to start asking these questions, you have to understand how these single particles behave, and this is exactly the domain of quantum mechanics. I mean, like they've studied this for like 100 years, and they know exactly how one particle behaves, and it's according to the laws of quantum mechanics, which I'll tell you a little bit about today. So, right, if you have like one particle and you want to decide you're going to store logically a bit with it, then you need some kind of property of that particle that can take on one of two possibilities. And there are actually many choices, many things you can try, and many things people have tried in their attempts to build a quantum computer. So like, I'm told that like a hydrogen atom has one electron, is that right? And perhaps it can be like in this like ground state where it's like orbiting near the nucleus, or maybe in an excited state where it's orbiting farther from the nucleus. So in some sense, this position, you can just say, well, we'll call this 0 and we'll call this 1, and that'll be how we'll try to store our bit. Electrons, you can do a different thing with an electron. Electrons have a thing called spin, I'm told. What is this? I don't know. I don't know if anybody exactly knows. Some kind of analog of angular momentum. But anyway, an electron's spin can either be up or down. One sec. And you can somehow use magnetic field to detect this. So great. So then you can just say, all right, spin up, we'll call that 0, and spin down, we'll call it 1. Do you have a?
The way I was told was Earth spins around its own axis.
Yeah.
And that's the intrinsic spin of Earth.
Yeah.
Electrons have a similar thing. And the reason you can detect a magnet is because moving electricity generates magnetic field.
Yeah, I've heard this description too, but then I've also heard people say, well, it's not really like that.
Yeah, it's
so
not really
I don't really know what to believe. So I just take their word for it that there's some property called spin. And maybe that's just, it is what it is. But yeah, it's something. It's something. There's one that I think you've genuinely heard of, which is the one I'll prefer to talk about actually. Let's say instead you have a photon. Photons have a property called polarization, or linear polarization. And you've actually probably interacted with this. So basically, a photon can be either horizontally polarized, just like this, or vertically polarized, like this. And you can get these polarizing filters if you have a camera. That black piece of plastic is actually called a Polaroid, and you put it in front of the camera and it filters some of the light. And it's to do with it filters one of these kinds of polarizations. We'll talk about it in a second. Yeah, or you buy sunglasses and they have polarizing sunglasses to block light. Or if you go to the 3D movies, they have one is a horizontal filter polarization, the other is vertical, so you can get two different images for your eyes. So yeah, this is a concept you've even dealt with in life. Yes?
Yeah, so why are there only two possibilities for direction? Because in 3D there should be 3 or something. I mean, I don't know physics as well. But
yeah, I don't know, but apparently there is. There's two dimensions of polarization, linear polarization. Again, I don't promise to know these things, the physics of them very well, but for different particles, there are various properties that they have, where they have 2 properties. It's a good question. So anyway, let's take this last one, as I said, and photon polarization, just an example of how you might try to get a logical bit from one particle. And again, take my word for it. You can build a machine. A physicist in a lab can build a machine, which we'll call a measuring device, for a polarization. So perhaps it looks like some kind of, I don't know, a box. And let's put a little hole in here. And then a photon is, you can shoot a photon into this hole. And then it has some digital readout, like a screen up here, an LCD or something. And then you fire a photon in, and it either says horizontal or vertical. Okay? You can build a physical box that has this property. Okay? Call that a measuring device. I guess in the olden days, there are detectors instead of an LCD readout, they'd have some kind of dial and a needle, maybe it would point to H or V. So this is actually how normally, in a diagram, they draw a measuring device with this a needle pointing to the outcome. So we'll do that too. Great. So you might think, wonderful. Let's do it. Let's say horizontal is 0 and vertical is 1. And then hopefully we can build some other devices that switch polarization and manipulate them, and we can build a computer. Well, not so fast. Yes?
There's no middle wall constitution here, right? This is some property that's discrete about the photon?
In a sense, yes, but now wait for what I'm about to say. Yeah. Okay. So I will now tell you the first law of quantum mechanics. So quantum mechanics, law number 1. So if a particle, I'll put that in quotes, and actually this can be a collection of particles or any quantum system, one, I don't know, quantum system, I guess, that's governed by the laws of quantum mechanics. Let's just call it a particle. If it can be in one of 2 basic states, okay, such as in these examples, and let me just call these basic states 0 or 1. Okay, and that might be its spin or its polarization or its energy level. Also, let me do a bizarre thing and put weird asymmetrical brackets around these 2 things. I'll explain that later. It's just some symbols for now. Yeah, so if a particle can be in one of 2 basic states, 0 and 1, then it can also be in a so-called superposition of these states. Meaning, I'm running out of space, so I'll go to the next board. Okay. Meaning that its state can also be described like this. Alpha amplitude on 0 and beta amplitude on 1, where alpha and beta are numbers satisfying a little equation. Alpha squared plus beta squared equals 1.
So both alpha and beta can be complex numbers?
Yes, you're spoiling everything. Yeah, no. Yes, complex numbers, as it turns out. Which is why I wrote these little bars around alpha and beta. Okay, and such a particle or such a state is called a qubit. Okay, so this is just a fact of quantum mechanics that when you have like two basic states or two, different possibilities, that like the correct definition of the state of a particle is a superposition. Alpha, quote unquote, amplitude on 0, beta, quote unquote, amplitude on 1, where these numbers satisfy the squares add up to 1. Okay? And what does amplitude mean? Just take it as a word. It's like some word that describes these two numbers. It's not a probability, for example. It's just, it is what it is. Okay? So, for example, just for concreteness, stick with this photon and polarization, where 0 means, quote unquote, horizontal polarization, and vertical means, 1 means vertical polarization. If you have just like a photon hanging out, a photon might have state like 0.8 amplitude on 0 and 0.6 amplitude on 1. Okay, that expression in quotes is like the state of the photon. Yep?
How is this even kind of discrete then? Like, in what sense was the answer to my previous question yes?
Well, it's discrete in the sense that there's two things on which you have amplitude. For example, this is how quantum computation people like to start to tell you about the laws of quantum mechanics, and it's nice and simple. In physics, if you want to like get to page 1 of like quantum mechanics, they'll treat like the basic states of a, let's say, a photon as like a position. Let's say along the real axis, a photon's going here, and then there's like uncountably many basic states, and you have like a superposition over, all the, points on the real line, and that's very painful. For example, Professor Griffiths has a textbook about quantum mechanics, and like they first get to qubits on page like 320, and they start with a harder case where you have like superpositions over the real line. But for us, it'll just be 2, typically. Okay, so that's a possible state of a photon. Let me just check. I didn't pick those numbers randomly. It's a little Pythagorean triple thing. 0.8 squared plus 0.6 squared, 0.64 plus 0.36, which is 1. Okay? So that's, you can have a photon in that state, but you can also have a photon in this state, 0.8 amplitude on 0 and negative 0.6 amplitude on 1. That's perfectly possible. And these are two different states. And just, I could say again, like, these are not probabilities. They don't add up to 1. They're not even positive. They're something. Okay, let me do another example. So you can also have 1 amplitude on 0 and 0 amplitude on 1. It's kind of convenient that I have like the two basic states written in these funny brackets to distinguish them from numbers. Okay, 1 squared plus 0 squared is 1. And this particular state is sometimes just called 0, for reasons we'll eventually see. Sort of like, purely or 100% horizontally polarized. But for yet another example, you can also have I amplitude on 0 and 0 amplitude on 1. Or this is, the complex number, square root of negative 1. And indeed, it's like a little check of this, like the magnitude of I is 1 squared plus, the magnitude of 0 squared, 1 plus 0, which is 1. Okay, so all of these are, valid states of a photon's polarization. Okay, and similarly, if you have an electron spin, it can have like, 0.8 amplitude on spin up and minus 0.6 amplitude on spin down. Just a word on complex numbers. I'm already introducing like some weird concepts, and like I'm going to introduce more weird concepts. So like, so as we're not like stressing about too many things simultaneously, like in basically all my examples, I'll only use real amplitudes. I'll definitely like to use negative amplitudes. That's important. But it's almost actually for the purpose of quantum computation, you can actually show a theorem saying that like without loss of generality, you can assume all amplitudes are real. You might not want to actually do that, but just to reassure you that it's enough mainly to think about real amplitudes. Okay. So that's, now I've told you the truth about like what state a photon can be in. But I also told you like this physical box exists, like this measuring device exists. So now you might fairly ask, well, I mean, you know, what happens if you take a particle that's like in, let's say, this state, a photon that's in this state, and like fire it into the box, this measuring device? I mean, the LCD readout can only say horizontal or vertical, but it's in this superposition. So what happens? Well, that's the subject of quantum mechanics law 2. It's basically going to be 3 laws, but I won't even get to the third one until next lecture. So that tells us what happens when you measure a particle which has 2 basic states. So I'm using this phrase, I don't even know if it's real terminology, quote unquote basic states, to like refer to like 0 and 1, like horizontal and vertical polarization, or spin up and spin down. Whereas state refers to like all of these myriad possibilities. Okay, so for a particle with this state, alpha amplitude on 0 and beta amplitude on 1. If you measure it, then, well, here's the rule. With probability magnitude of alpha squared, the readout will show, 0. And with probability magnitude of beta squared, the readout will show 1. Okay, if this is your polarization measuring device, 0 is code for horizontal and 1 is code for vertical. Okay, so you fire this particular photon, or photon in this particular state, into this measuring device, for example, then there'll be like a 64% chance the readout is horizontal, and a 36% chance that it's vertical. Okay. There's actually an and that goes at the end of this quantum law too, which I'll say in a moment, but let me pause for 1 second to say a few other things. First of all, it's a deep question and like philosophical question, like interpretation question in quantum mechanics. What exactly does it mean to measure a particle? And basically, we're not going to get into it. Maybe I'll talk about it, philosophically much later. But just take your word for it, my word for it, that physicists can build these things called measuring devices for all these properties. And quantum mechanics says that they have this behavior. Okay, so for the question of like what exactly is a measuring device, the physicists, just like that pornography definition, right? It's like you know it when you see it. So they know what it means to like have a measuring device, and quantum mechanics says that it obeys these rules. And also, it's like a teeny bit of a callback to the previous lecture. If you remember Thursday's lecture, where I was talking about how like, you can store a list of numbers using like the state of some particles. And then, maybe Fourier transform it, and then like when you measure it, you get samples from f hat. With 1 qubit, with 1 particle, you can store a list of 2 numbers. Okay, and this alpha would be called f of 0, and this beta would be called f of 1. That's my little, or it's a function mapping just 0 and 1, 2 positions into a complex number. Okay, and if I was really tough, like I would actually just use this notation throughout, but it's very traditional to use alpha and beta for the amplitude, so I will. Okay, so I said there was an and. Quantum mechanics law 2 is not quite done, and you may have heard about or like know a little bit about this second part, and I mentioned it last time. Once you measure a particle, that changes its state. And basically, it changes it to the state which the measuring device happened to read out. Okay, so this is the conclusion. If the readout showed 0, like the particle state changes to, like, 1 amplitude on 0 and 0 amplitude on 1. I know it's a little confusing. You have different kinds of 0s and 1s. Else, if the readout showed 1, let me just, for brevity, say the reverse. The particle state changes to no amplitude on 0 and 1 amplitude on 1. Okay. So that's 2 sort of consequences of measuring. Actually, when you look at this box that I drew, it kind of looks like the photon goes in there and gets measured and then dies in the box somehow. And actually, it's not so bad if you're studying quantum computing to even forget about this and just assume that when you measure a particle, it does kind of die and you can never touch it again. Because again, actually, without loss of generality for quantum computing, you may as well take that as your model. But nevertheless, in real life, a photon doesn't just disappear. It continues on in life with this changed state. So maybe you should imagine there's another, I don't know, slit here, and the photon goes through the measuring device. It reads out on its LCD, horizontal or vertical, and then the photon continues on its way, but in the new state. Yes?
Yeah, okay. So maybe it's more going to a philosophical question, but still, is it the photon changing state because the measuring device is working in this way? It's measuring device actually changing its state somehow using physical things to measure the photon? Or the question probably is could it possibly be that we can we can build a measuring device that reads alpha and beta without changing the state of the photon?
The short answer to your question is the second thing, no, we can't. The measuring device, the act of measuring this photon necessarily changes its state.
Okay. Well, the first part.
Yeah. Oh, that was the first part, right?
No, the first question about
you said
actually measuring device changing the state itself or the photon changing it? Okay. Sorry. Yeah.
By virtue, all I can say is by virtue of the photon interacting with the measuring device, the state of the photon changes.
Okay, always. Okay.
But I agree. I mean, if you sit there and think about it, you may have many questions, and basically these questions are unanswered. Yeah?
Is it possible for the photon to go back to a non-deterministic mixed state at some point in time?
You used a phrase which we'll get to in lecture 17 or 18, mixed state. For the first 16 lectures, we're only going to talk about so-called pure states, which means, well, this thing that I've put up here. So if your question is about the distinction between those two.
I mean, will it ever get back to one of these 0.8, 0.6 states?
Yeah.
That's an indeterministic state?
Yeah, it certainly can.
Okay.
Yeah. So this 0.8, despite the weird sounding terminology, this 0.8, 0.6 thing is a pure state. If you don't know, you can forget I said that anyway. But yeah, it's perfectly possible for the photon's state to subsequently later change to something like this. And in fact, next lecture we'll talk about changing the state of photons and or particles and in which way a qubit state is allowed to change. And basically, in a lab, they're pretty good these days for most different physical ways of implementing a qubit. They can kind of change it to whatever state they want, pretty much. Yes?
So you mentioned, I know you mentioned earlier without loss, we can do everything with real numbers, right? Is that true?
If your only goal is to build a general purpose quantum computer, then you can make a quantum computer where all the amplitudes remain real numbers.
Okay, so I guess without loss, phase doesn't matter either. If you just had a -0 there, would you also say this is essentially just a 0?
We'll get to that. You're also a person that's knows a little bit of quantum mechanics, obviously. Yes, I'll eventually come to talk about this, but there is a sense in which, if I put negative and negative here, it's the same state as without the negative. But let's not worry about that for now and treat them as different states. Like this state and this state are definitely distinct.
So when you say it changes to one amplitude, is that it's the same thing if I like? Sorry if this is just saying the same question, but like you say after measuring it's like collapsing to one amplitude, it would be the same if I said it collapsed to negative one amplitude.
Yes, we'll eventually later see that like due to the mathematics of quantum mechanics, it would all be the same. There's no way to like distinguish this state from this state. But for now, let's just assume that they're potentially different states. That's a very technical point, but it's a good point. Okay. Any more questions? Yep.
So could you, in principle, just keep measuring a photon just because you want to keep it in this deterministic state forever?
Oh, very good. Yeah. What you talked about is called the quantum Zeno effect. You'll hear a little bit about it on the homework. It was something that like was pointed out first by Alan Turing. And it was that basically, like, if you really want to hold, a photon state at like horizontal, let's say it comes out of here and it showed horizontal, then you just like keep measuring it, and you will like hold its state at 0. In fact, I'll mention exactly that just now. So let me do it. Let me erase this. Hopefully you remember it. Oh, I should of course have mentioned this makes sense because by definition of a quantum state, these two numbers add up to 1. So these are non-negative numbers. They add up to 1. So it like makes mathematical sense to say with probability this happens, and with the remaining probability that happens. Should have emphasized that. Okay, good. So let's actually draw a little picture to illustrate Alp's question. Let's say we had the photon that was in this state, and it passed it through this measuring device, and it happened to be the case, and this is the 64% chance, that the measuring device said horizontal. Then, at this point, the photon state is what's sometimes called, in short form, just 0. But really, this means amplitude 1 on 0, and amplitude 0 on 1. 0 being horizontal and 1 being vertical. So that photon is still around. And if you just build a second copy of this machine, then it will always read out horizontal. Okay, because the state will definitely just be 100% I was going to say, 1 amplitude on 0. And so then by the law I just erased, there's like a 1 squared equals 1 chance that it will be read out as horizontal here. And it'll change state, or its state will collapse back to this again. Okay, so if you just chain together a bunch of measuring devices, it would just consistently measure it as 0, as horizontal. Horizontal equals 0 in my little story here. You look worried, is that?
You said that the photon could go back to a superposition state, and we can force it to be any state we want or something like that.
With sufficient, yeah. I mean, there are like other physical things you can do to this photon, like fire a laser at it or make it go through some weird prism or something that will cause its state to change.
But let's say we leave it be. Like,
Yes.
Then would it stay like that?
Let's say yes, yeah. It's assumed when we get to so eventually we're going to talk about quantum computing, which is kind of like a theoretical model of the physics, much in the way that you draw like a circuit diagram, a Boolean circuit with ands and ors and not gates, and you just assume that it works according to very simple laws. Okay, in actual physical reality, you have to be careful that the wires are insulated or whatever. That might change the state. But yeah, at a high level, yes, we assume that this photon just stays in the state 0 unless something else affects it.
So why do we bother with buying infinitely many measuring devices if we can just put the photon in a box and leave it be?
Well, first of all, photons don't like to stay in boxes, right? They like to fly along, so they're going to start affecting things. But yeah, that thing I mentioned is if you imagine that some kind of external field, external physical thing was constantly affecting your photon, and you're trying to fight against that. But in our these models, these simple models we draw on the blackboard, we just assume that the state does not change. Yeah?
So you said that scientists now can produce any photon?
Roughly.
Okay. I was gonna ask like, since alpha and beta can be like real numbers, like to what precision can you like create these alphas and betas?
I mean, it's the same question as if I asked you, build me a slab of silver that's pi meters long. Well, you could try to make it 3 meters and 14 centimeters, and if you're really good in the lab, you can get it 3.141 meters, and if you're really good in the lab, you can get 3.1415 meters, and it goes like that. Good. Yeah, so the cool thing about, what I like about polarization is you can actually illustrate it with like physical devices you can hold in your hand and buy off Amazon for $1. So there's this thing, I have here like from the last time my kids went to some 3D movie, like this is like the glasses they give you, right? One of the lenses has popped out. And this piece of black plastic is like, it's very much like, it's called a polarizing filter. It's very much like this measuring device. Except it's exactly like this measuring device, plus after it quote unquote measures, it does like sort of like an if then else statement. So at high level, this thing, let's say this horizontal filter that comes in your movie 3D glasses, it works like this. So if a photon comes in, then it does two things. The actual physical physics of it, I'm not even sure how it works, but like at a high logical level, it works like this. One, it measures, in this sense, the photon. Its polarization state, and therefore either gets horizontal, which we'll call 0, or 1. Okay. You can also think of this measurement as like converting like a quantum piece of information into like a classical bit of information. Right? This readout, this LCD readout, is like showing one classical bit. So it does this, and that as per the corollary, like changes the state of the photon to whichever was the measurement outcome. And then it has the following secondary physical effect. If the state, or rather if the measurement, the readout if you will, was 0, aka horizontal, then the photon flies through in its new state. Else, the photon gets absorbed. So somehow, like, the photon is converted to heat and does not fly through. Okay, I don't know the exact physics of it, chemical engineering of it, but just take it, this horizontal filter, as like a physical device that does these two things. Okay. So for example, let's say you take a laser pointer and you point it through the lens. Now, I don't want to get into this part, but like you can think of the millions of photons coming into the laser pointer as having some kind of like random state. And so you might reasonably guess, therefore, that when they hit the filter and get measured, there's like a 50% chance that they're 0 and a 50% chance they get measured as 1. Okay? Just accept that. Like, it's not quite following the rules I said. Right. So in particular, like 50% of the intensity of the laser pointer gets through the filter. And it's a filter, right? That's why you have it for your camera, right? It like blocks some of the light coming into your camera. And what's nice about that is all the photons that do get through are sort of definitely in the horizontally polarized state, or definitely in the 0 state. So it's kind of like you've like initialized a bunch of photons to be in like the 0 state. And then, well, actually, when you talk about quantum computing, that'll be like a basic assumption that we can just like say, all right, let's start all our photons or particles in the state 0. And this is like a physical way you could imagine this happening. Okay. Great. There actually also exists another physical device called the vertical filter, which maybe, well, let me draw it like this. It's the thing that's in the other eye of the 3D glasses. And its definition, if you will, is very much like this. It also exactly does 1, but then it just swaps these two. So if the measurement turned out to be horizontal, then the photon just turns into heat. And if it was vertical, it like turns, it flies through. Okay, so you can use this to like, initialize photons to 1. There's one more thing that's cool, which happens to be true about these two objects, which is that if you have this object and you want this object, you can get it in real life just by literally turning the object 90 degrees. Okay, so like they have the same black plastic in like these glasses, and like they take the sheet and they like put one eye like this, and then they turn the sheet and cut out another eye hole and put it here, right? And that's how the 3D effect works, right? The movie screen projects one image with horizontally polarized photons, and the other image with vertically polarized photons. And so like, the horizontally polarized ones, they go through your left eye because of this, but not through your right eye, and vice versa. So your two eyes see two different images. Okay? So I have here two, so you can try it. This is a laser pointer. Hopefully it didn't run out of batteries. Maybe it did. No, it's OK. So who wants to try it in the privacy of their seat? All right, great, yeah. So you can pass it around if you want. So like I punched out the same eye. So like these are either both horizontal or both vertical. So if you want to try this, you can like line them up and shine the laser pointer through, and it should go through like as bright as if you only did one. But if you do this and shine it through, you should get it to be able to block it, so like it doesn't go through at all. And of course, I have no need to remind you, like you need to also put like a white sheet there so that you can see or not see the red dot as you're doing it.
Which button does the thing? The front button?
Yeah.
The red button. The red button does it. Okay.
No, it just reboots the
Okay, you can try this. You can try this at home. You can buy this like Polaroid sheet for like 50 cents on Amazon. You might also ask, like, hey, what happens if you turn it like 45 degrees? Oh, I'll tell you about that later. OK, let's get back to the math. So one thing I have to tell you is this is all about a qubit when there's two quote-unquote basic states. It's also perfectly possible to have like a particle property with 3 basic states. For example, like if you have your hydrogen atom, like I think the electron can have like 3 positions if it's like this is the super excited state. Or apparently, I had to look this up on the internet, if you have a deuterium, hey, don't point it at me. If you have like a deuterium atom, then its nucleus can have a spin, which is one of 3 possibilities. OK, so that's perfectly fine. And we usually call the 3 possibilities 1, 2, and 3. And this is called a Q-trit. OK, by analogy with the trit in basic computing. And you can also have a particle with 4 properties, or 4 basic states, in which case it's most common to call them 1, 2, 3, and 4. And do you know what this one is called? It's a trick question. It's called a Qubit with d equals 4. Okay, so in general, we're not going to keep inventing letters here. So anything with more than actually even 2 states, instead of calling it a qubit, they call it a qudit. And you also specify what is the d, which is the number of basic states. Or as we'll see, it's the dimension. Okay, this is also sometimes called a d-level system. This is called a 3-level system because I don't know, there's 3 levels. And actually, this one is particularly interesting. The most common way is not to have some weird particle with 4 different kinds of spin, which I think theoretically exists, but I don't know if it exists in the real world practice. The most common way to have this thing is to just have 2 photons. And if you have 2 photons, then you can kind of consider them to be a joint quantum system or a superparticle. And yeah, I mean, if they're both horizontally polarized, you call that 0, 0. And if they're horizontal vertical, it's called 0, 1. Okay, 1, 0, and 1, 1. If they're both vertical. Okay, or you could call these 4 possibilities 1, 2, 3, 4. It's fine. Right. So I bring this up because sometimes we'll talk about like, higher level systems or like Qubits. We'll mainly talk about qubits, but it's good to know that Qubits also exist. And there's sort of the quote-unquote obvious extension of the quantum mechanics laws 1 and 2. I'll kind of just write it briefly. Let me say law 1 becomes, the general state of a qubit looks like, amplitude alpha 1 on basic state 1, amplitude alpha 2 on 2, etc., down to amplitude alpha d on d, such that, and these numbers, magnitudes, should add up to 1. And quantum mechanics law 2 also extends in like the very natural way. If you have a measuring device for these basic states, then it'll have d different possible things it can read out on its screen. And it'll have readout, quote unquote, I with probability magnitude of alpha I squared. Okay, and against that makes sense because this is a positive number or non-negative number, and all the probabilities add up to 1. Okay, and and when this happens, the state changes to or collapses to alpha I is 1 and the rest are 0. That's the new state, like quote unquote all 1 of its amplitude on the outcome that was measured. Okay, so this is just the higher D generalization of the qubit case.
So we don't need this because 2 is enough.
Pardon me?
But we probably don't need more than 2 states because 2 is enough.
Maybe you mean for the purposes of quantum computing?
Yeah.
Yeah, so for the truth of what goes on in life and in physics, like this is the situation. In quantum computing, just in the same way, like we decided, and it's very convenient, like when we were talking about computing and Boolean circuits, to just have 2 bits, 0 and 1. Same with quantum computing. With classical computing, you can like have trits, like low, medium, and high voltage, and some kind of weird like basic gates that worked on trits. But you can do it, but we generally don't. It doesn't buy you much. Yeah.
Yeah, so when you said that we can use 2 qubits to simulate the 4 basic states,
Yeah.
you also know, like, let's say 1 qubit has alpha and beta, and another one has like whatever, alpha 2, beta 2. Can you like know those 4 parameters?
We'll talk about that next class. That's a good question. So like if you have 2 photons and each has their own alpha and beta, and then you just decide to like put them next to each other and say, this is a qubit with d equals 4. What are its 4 alphas? Tell you next time. It's the tensor product of the two-dimensional vectors. But yeah. Speaking of vectors, now is the time to really hit the math. Okay, so now we're really going to enter into the math of qubits, or qudits. So the state of a qudit, it's like d complex numbers. And how do we like to arrange d complex numbers? We like to put them into a vector. Okay, so instead of like writing the state as this like phrase, we'll just put it all into a vector. Okay, so a qudit state, we like to make it into a column vector. Alpha d, it's a d-dimensional vector. Technically, these can be complex numbers, so it's in c to the d, not r to the d. And we always like to consider it to be a column vector. And for now, let me call this v, as is standard in math. This is very untraditional in quantum, so we're going to stop calling it v relatively soon. But for now, we'll call it v vector. And it's not just any old vector like this, right? It has this property, which is that the sums of the squares of the coordinates, magnitudes, I say that in parenthesis because you have to say that if they're complex numbers, but if they're real numbers, it's just the squares, is 1. And that means this quantity is, in math, literally it's the length of this vector squared, right? That's the Pythagorean theorem. So this means that a state is a unit vector. Okay, a unit vector is a vector of length 1. Okay, so a Qubit state is just any complex vector, d-dimensional vector, that's of length 1, a unit vector. Okay? So let me go back for a while to Qubits because they're our favorite case. So that's when d is 2. So these are little short column vectors of height 2. So, an example Qubit state, which we used to call 0.8 amplitude on 0 and 0.6 amplitude on 1. Well, now we'll just call that the vector 0.8, 0.6. Okay? And we also really like to draw this. Okay? It's very important, actually, to understand the sort of geometric, it's not such a great circle, picture of qubits. They're just a two-dimensional vector. So, 0.8 is like out here. This is 1. And 0.6 is maybe here. Well, you know what I mean. So this vector might be this. Okay, so that's 0.8. That's 0.6. Okay, and you think of that vector as also standing for the qubits state. And in fact, this is the unit circle, all the vectors in 2 dimensions of length 1. So like every point on this unit circle, or every vector pointing to this unit circle, is a qubit state. Actually, what I've said here is like a little bit misleading because I've drawn you a picture of the 2-dimensional real plane. And of course, complex numbers can be amplitude. So actually, qubit is actually defined by 2 complex numbers. Again, this is very annoying, but that's life. So let me briefly recall. You'll work a little bit harder on complex numbers in your homework just to remind yourself. But I will recall for you now that if z is a complex number, which is like x plus I times y, where x and y are real, and I is the square root of -1. Its magnitude, this thing that's showing up here, the magnitude of the complex number, is, well, let me say what its magnitude squared is. It's x squared plus y squared. Okay? The sum of the squares of the real and imaginary parts. Let me just also remind you that this is, if you, do FOIL, it's the same as this, x plus iy times x minus iy. And I write it like that because this is like z times the complex conjugate of z. Okay? I hope you remember all this stuff. Z star, which actually is equally often written z bar, but I slightly prefer star, is the complex conjugate. You flip the sign of the imaginary part. Okay, and that's what the magnitude squared of a complex number is. So in particular, like when these are genuine complex numbers, they should have the property that the sum of the squares of their real parts and the squares of their imaginary parts add up to 1. As I said, I'm going to try to focus on just real amplitudes. But I bring this up now with this picture on the board because, to stress what is the most annoyingly confusing thing that happens in the elementary, math of quantum mechanics and qubits. Okay, confusion. On one hand, we really like to think of one qubit as being defined by 2 numbers, right? The 2 amplitudes. Great. On the other hand, when you're in 10th grade or whatever, and you're learning about complex numbers, you're like, oh, one complex number, you can really think about it as 2 real numbers. And, you illustrate one complex number in the plane with a picture that looks like this. This would stand for 0.8 plus 0.6 I. So it's weird that you want to draw the same picture for both cases. Now you can't really do this because one qubit is technically 2 complex numbers to find its amplitudes, and therefore it's actually 4 real numbers to find 1 qubit. But we cannot draw a picture in 4 dimensions, which is annoying. So we really like to just pretend the amplitudes are real and try to draw our pictures in the plane. So we have this general question, like what should we do to resolve this? And let's keep it real. So what we're going to do is we're pretty much only going to do this. Okay? I'm really going to try to pretend that numbers are mostly not complex numbers. And when I have a qubit, I'm going to mostly try to pretend that its amplitudes are real numbers, because the overarching factor is it's really nice and helpful to think about one qubit geometrically as like a point on the unit circle in the plane. Okay? Great. Okay, well, more math, as it turns out, more linear algebra review. So here we go. Okay, so qubit states are unit vectors. Actually, qubit states are unit vectors. We really like to talk about unit vectors a lot in quantum computation. So a unit vector, v, satisfies that 1 is the squared length of v. And another way to write this is the inner product of v with itself. Okay, I hope you all know this. This is my notation for the inner product, or the dot product. And the dot product of a vector with itself is the square of its length. And we're going to be talking about inner products a lot too. So it's very good to think about the meaning of the inner product. U vector, v vector. Okay, let's say you have two vectors. Let's say not necessarily unit vectors. What does it mean, their inner product or their dot product? Well, I hope you know, but I'll remind you of some things. So one thing it means, this is a number, of course. It's the length of u vector times the length of the projection of v vector on u vector. Let me draw a picture. If this is u vector, and this is v vector. Okay, wait, let me get this in the right order. Yeah, that's fine. Okay, the length of u is what it is, and then the projection, this is like the projection. This is the projection. Okay, it's actually signed, so I mean, if it's pointing this way, it would be negative. And this is actually the best way to think about the inner product. This is how, overall, I want you to think about the inner product. Particular, a couple of points. If these two vectors are perpendicular, then the projection of one on the other is the 0 vector. So the inner product is 0 if they're perpendicular. And if they're the same vector, like v and v, then the projection of v on v is just again v, and that's why this equation holds. Okay. That's meaning number 1 of the inner product. Put a symbol of theta in there for the angle between the two vectors, because that comes up in meaning number 2. Meaning 2 is it's the length of u times the length of v times the cosine of the angle between the two vectors. And by the way, this is just cosine if u and v are unit vectors, which they often will be. Okay, so when you have two unit vectors, their inner product is the cosine of the angle between them. That's going to be important for us. And finally, the third definition or meaning or equality is that it's this quantity, u1 v1 plus u2 v2 plus dot 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 plus u d v d. Actually, let me for a second specify that these are real vectors. If they're not real vectors, then maybe it's not exactly even clear what does it mean, the angle between them. So let me just, we mainly like to think about real numbers, so let's think about them as real vectors. Okay, this is like the normal formula, right, for the dot product. And it's also going to be important to note that there's a different way to write the same formula. Some kind of weird matrix product where you take u as a row vector and v as a column vector and multiply them. This will give you like a 1-by-1 matrix, or just a number, and that number is this number. Okay, so this is also the inner product between u and v, the dot product. And this is like u transpose v. Okay, because our vectors are typically column vectors, so U transpose is the row version. So far, so good? This is another annoying thing I have to now tell you, but as I said, this is all for the case of real vectors. There's like a weird twist, which you might have forgotten from linear algebra class when they're complex vectors. When they're complex vectors, you see, you really, oh, I shouldn't have erased this thing, but remember that. When they're complex vectors, you really, really want this to be true. You want this to always be true, this formula right here. But it's not true if they're complex numbers, according to this formula. Right? If you plug in v here, you get the sum of the squares of the entries of v. But that's not the length. You need the sum of the squares of the magnitudes of the v's. So that's why, if you remember sophisticated linear algebra, the real definition of the inner product is similar, but you have to put a complex conjugate sign on all the u's. And why do you do that? It's so that, you know, when u equals v, this will be the magnitude squared of, I really shouldn't have erased this. I'm using this fact right here. Okay, this will be the magnitude squared of v1 plus dot 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 the magnitude of vd squared. Yeah?
For clarification, so are we considering one vector to be like alpha and beta, or like is one vector one qubit?
One vector here is one qubit. So a d-dimensional generalization of a bit. So for qubits, which again is the main thing that we'll be talking about, one v will typically be like alpha beta, a two-dimensional element of a two-dimensional vector. Yeah, good question. Right, so it'll occasionally come up. You'll have to remember this is the funny definition of a complex inner product. So again, over here, the real definition is not technically this, but it's to put these stars here. And so in fact, this is why I didn't quite draw this as a T. This symbol is a dagger. And the dagger means conjugate transpose. Okay, this is a very technical point. What this dagger means, you take the transpose of the matrix, or convert a column vector into a row vector, and you stick the complex conjugate on each entry. Okay, that's what dagger means. And actually, you can just retain this even as the definition for real vectors, because if you have real numbers, then doing the complex conjugate doesn't do anything. So it's back to normal. Okay. Any questions? All right. Good. So, more notation. So now, we've got the reminders of these little bit of elements of linear algebra. I'm going to tell you about something quantum mechanics people and quantum computer people love, which is Dirac's bra-ket notation. Okay. So I'd like to emphasize, actually, that this notation I'm about to show you is notation for linear algebra. It does not inherently have anything to do with quantum, although you mainly find it in like books and articles about quantum mechanics and quantum computing. But it's actually just a thing about linear algebra. And most people really, really hate it when they first see it. They're like, this is terrible. It's the worst thing ever. But then if you're like me, you actually come to really, really love it. So now I actually love this notation that I'm about to show you. And in fact, I use it whenever I'm doing linear algebra at all, like quantum, not quantum. Like, I love it so much. So I'll now tell it to you. It's like notation for vectors. So when you're in high school, I think, depending on what high school you go to, when they first introduced vectors, they use this weird notation, I'm told. They say I vector stands for 1, 0, 0. And j vector stands for 0, 1, 0. And k vector stands for 0, 0, 1. Okay? And then like the 3 unit vectors are like I, j, and k. Did at least some people see this in high school? I'm told, yeah, OK, good. All right. And then, like, you know, if you have like some generic vector, like 3D vector, like 3, 5, minus 2, you can say, oh, that's 3i plus 5j minus 2k. OK? All right, and then you get to college, and they're like, well, That's not so cool, and we need the letters I and j for other things. And also, we're going to be in d dimensions, not just 3 dimensions. So they give you some new notation where like E1 stands for like 1, 0, 0, dot, 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 0. And like E2 stands for 0, 1, 0, dot, 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 0. And in general, like EI stands for the vector that's mostly zeros, except for a 1 in the ith spot. And these are like the d standard basis vectors for d dimensions. Okay. And then when you get to quantum, like to heck with this, we're going to change the names of these objects. We're just going to call this one 1 inside weird asymmetric brackets, 2 inside these weird asymmetric brackets. This last one is called d inside weird asymmetric brackets. Okay? So these symbols actually just stand for these vectors. Okay? And it's assumed you like know what dimension you're in. There's an exception to this rule, and that exception occurs when d is 2. Because when d is 2, instead of calling them 1 and 2, you call them 0 and 1. Okay? Like when d is 2, you follow like the computer science Python convention of indexing your arrays by 0 rather than like the math convention by starting them with 1. Okay? So when d equals 2, you instead call them 0 and 1. Okay? But that just stands for this and 0, 1. Okay? So all along, this is the secret. This symbol means this particular vector in 2 dimensions, and this symbol means this particular vector in 2 dimensions. Okay? Or it could have been 1 and 2, but it's 0 and 1. Okay? And therefore, a general qubit state, which we're saying before was like alpha amplitude and beta amplitude. Just 5 minutes ago, I told you, oh, now it's a vector in 2 dimensions. It's still a vector in 2 dimensions, but now you can also write it like this: alpha times this vector plus beta times this vector. Okay, just like this, except it's in 2 dimensions. Okay, and when you like draw a picture of a qubit, as you often do, pretending its amplitudes are real usually, then like this guy, this particular qubit is 0, which is 1, 0. You sometimes name the axis after that too. And this particular qubit is 1, aka 0, 1. Okay, and if it's a qubit in d dimensions, then you switch back to this and call your dimensions or your basic directions 1, 2 up to d. Okay, any questions about that? Yep. Oh, I'll tell you. There's many reasons why I like it. One reason to like it, well, one reason to like doing this kind of thing in general, like to do this rather than this, is because, at least in quantum computing, you often have very sparse vectors. So instead of writing like a vector with like tons and tons of zeros and a few non-zero coordinates, you can just write the non-zero coordinates and like omit all the other ones. Okay, that doesn't explain this versus this. The reason this is better than this is you don't have to cram the whole number into a subscript, into like a tiny font. It's like right there in like normal display text. Okay, and you don't have to insert like a pointless extraneous letter E. You just put the subscript right there. So that's why it's great. In fact, it's really like, okay, when I was really young, like before you all were born, there was a programming language I learned called BASIC. QBasic. It came with DOS. And like if you wanted a variable to store a string, you gave it any like name you want with letters, and you put a $sign at the end. And the $sign signified that it's a string type. And this exact same thing here, except the type is column vector. Okay, so in general, the notation is that this means a column vector named blah. Okay, and that's actually another cool thing. You can put whatever you want here, like just whatever word you want, you can put it there. Okay? And like this symbol signifies the type of this object is column vector. Okay? I should write that. Okay, and then you reserve these special names, you know, when the inside name is 1 through d for these specific column vectors. And this thing is called, this is Dirac's doing, which this is not as cool. It's called a ket. Okay? Yeah, you'll see. This part is less cool. It's kind of silly. OK, so whenever you have one of these objects, you automatically get a second object, which is written like this with the backwards brackets. And this denotes the conjugate transpose. If you don't like convex numbers, just think of transpose of blah. Okay, in other words, it's literally blah dagger. Okay? Or mainly, if you think of a blah as a column vector, then this just means, oh, I want the row vector version with the conjugates. Okay, and this thing is called the bra. And I think Dirac was like, it's hilarious, like bra-ket, bra-ket. Anyway, that was what he decided. We rarely talk about bras, actually. It's mainly kets. So I'll just call them vectors. OK, so one last piece of notation, which actually goes together with this silly name. Remember I told you, OK, if you go back to normal linear algebra notation, the inner product of two vectors, u and v, was the dagger of u times v. Right, this dot is technically matrix multiplication. But now we have a different name, right? So we would also now call this is the bra version of u, and this is the ket version of v. So it's like this times this. Okay, and sometimes in multiplication, you don't bother to write the dot. And then, this is why it's technically new notation. You have two consecutive vertical lines. So you're like, let's just put it down to one vertical line. OK, so this means this, which in turn means the inner product between u and v. And this actually turns out to be quite pleasant as well, that you have this notation. OK, so that's a bunch of notation that you're obliged to get used to. OK, questions? All right, well, let me go through some examples. Well, we'll get into it. Let me tell you the name of everybody's third favorite qubit. Everybody's first two favorite qubits are these two. Okay? But people's third favorite qubit is this one. 1 over root 2 amplitude on 0 and 1 over root 2 amplitude on 1. It's kind of annoying. You can just think of it as 0.7, 0.7. I guess those squares only add up to 0.98, but close enough. Anyway, 1 over root 2, 1 over root 2, which now we also like to write like this: 1 over root 2 times 0 plus 1 over root 2 times 1. And we like to draw it. It's this thing that's exactly at 45 degrees. It's that qubit state. And it's so famous that it has a name. It's well, it's a ket, and its name is plus. Okay, so this is some other notation that you'll be obliged to get used to. And that's plus right there. And everybody's fourth favorite qubit is this one, and we'll stop at 4. This one is called minus. Okay, so this minus is 1 over root 2, 0 minus 1 over root 2, 1. Okay, everybody kind of used the notation. It's really, this thing is 0, this thing is 1, and these are two more orthogonal qubits.
Why do you have a separate notation for minus if it's just plus with the swap, whatever, bra?
It's okay. So first of all, it's not. So minus and plus are both column vectors. That's important. If you bra this, it will not be. It'll be a different type of object. And yeah, it's also not the transpose. It's just quite different. I mean, plus and minus are. Okay, this is a bit silly, but I can define them both simultaneously like this, where you have to choose the same sign in both cases. Okay, it's just two different vectors. And let's go back to quantum mechanics for a minute. If you just to remind you of this. Plus is a state that a particle might be in, and if you send a photon in this state into a measuring device, then what will happen, it'll pop out an answer, and that answer will be 0 with probability, well, the square of the first coordinate, the square of the first amplitude, which is a half, and 1 with probability the square of the second coordinate, which is also a half. And you'll see the same effect or behavior if you pop a qubit in this state into the same measuring device, because the square of negative 1 over root 2 is also a half, even though they're different states. So this particular measuring device does not sort of distinguish between the plus state and the minus state. But there exist physical measuring devices that do, just not this standard one. Let's even talk more generally about if you have a general qubit state. And I guess now I will reveal that, like, instead of v vector, the traditional name for a qubit state is psi. That's my Greek letter psi. And it's a ket, so I have to do this. OK, so if psi is some other, let me draw it over here. Some other qubit state, say this one, where this angle is theta, then what are the two coordinates of psi, or the amplitudes? Yeah, I guess you all know. It's cos theta and sine theta. This distance is cos. The other one is sine. OK. So we can also write it like this. Cos theta times 0 plus sine theta times 1. OK, and so if you fed a qubit in this state into your measuring device, like the probability that you'd see 0 on the readout would be, well, the square of the first coordinate. OK, this is very important to remember, actually. So by the way, remember that this is 0. So when you take psi and you measure it, the probability that the readout, and also what the state changes to, is 0, is the square of the cosine of the angle between the state and sort of the readout thing. And in fact, the probability you'll see 1, well, on one hand, it's sine squared, because it's the square of the second coordinate. But it's also, if you remember a teeny bit about trigonometric identities, it's also the cosine of the angle between psi and 1. It's the cosine of pi over 2 minus theta squared. Okay, that's a little trig for you. In fact, let me do the same thing I just did. Take a general qubit state, psi, and figure out the, probability of measurement outcomes. But with different notation. Yeah?
So if we could just label any state by a theta, why do we go through all this trouble to label them in terms of these basis states?
Well, that's very convenient for qubits with real amplitudes. You can describe them by one real number, the angle. Technically, if they're complex, you can't just describe them by one angle. You actually need 3 real numbers to describe one fully general qubit. And it also makes less sense if it's like higher dimensional. But it is true, we're going to be focusing a lot on one qubit with real amplitudes, in which case it is fully characterized by like one angle theta.
So why do you need 3 numbers?
Well, there's 4 real degrees of freedom, the real and imaginary parts of the 2 amplitudes. And then you lose 1 degree of freedom because the sum of the squares is 1. OK. What if I just say you have some qubit psi, and you want to write it as some amount on 0 plus some amount on 1? What is this some amount? Well, it's the inner product of psi with 0, right? It's the inner product of psi with, it's like psi inner producted with 1, 0, right? That picks out the first coordinate. Or it's the length of the projection onto the horizontal axis. And we have new notation for that, right? This amount is the inner product between the 0 vector and psi. And this is this inner product. Okay, so you should get used to that. Okay, so in particular, like if you fire this guy into a measurement device, the probability of measuring it to be 0, you can also write it as the magnitude of this inner product squared. Okay. Okay, we have to do one more math topic, and then we're done. Actually, if I have time, I'll mention a teeny experiment you can do with the laser pointer. This topic is measuring in a different basis. Okay, let me draw a picture. Say we have a generic psi state, and this is 0. This is 1. Okay, we know that if we put this psi into the measuring device, we get either 0 or 1, and like these are the two probabilities. Okay, or it's the probability of measuring 0 is this, and the other one is this. It's the squared length of the projection of psi on the two different readout outcomes. So it turns out, just as I told you at the very beginning, like there exists a physical box you can build which measures photons in this way. You can build other kinds of boxes. And in fact, for any orthonormal basis of 2 dimensions, which is really just a fancy way of saying for any pair of perpendicular unit vectors, such as, for example, try to draw it generically here, this and this. Well, let me use quantum notation and call them kets. You can build a measuring device for this basis. Okay, just believe me. For every 2 vectors, in this plane, you can build a measuring device which measures with respect to that basis.
Can we just like rotate the device we already have?
Not in general. It turns out with the 3D glasses thing, basically yes. Okay, that's the other funny thing. I'll show you next time, like a fun experiment you can do with 3 lenses, and like you rotate one 45 degrees. Yeah, but in general, you have to build like a different kind of device. Okay. And I'll just tell you its properties. And I guess we'll be out of time. So it looks like this. It can accept a particle or a photon or whatever, and it has a dial or a readout, and it can point to either U or V. Okay, so the little LED screen on this, instead of shouting out 0 or 1, or horizontal or vertical, it shouts out either U or V. And it has this behavior. The readout is quote unquote U with probability. The length squared of the projection of psi onto U. Okay, which is like the squared length of this. And the readout is the other one, V, with probability the squared length of the projection of psi onto V. So this squared length of this. Okay, so really, what does it do? It takes psi and just writes it in UV coordinates rather than good old-fashioned 0, 1 coordinates. And then it does like the old measurement rule. Okay, so the squared length of psi in the UV basis, those 2 squared lengths give you the 2 probabilities. And as always, the state changes to the measured state. Yep.
Does this have to be an orthogonal basis?
Yes, it has to be an orthogonal basis of unit vectors. Okay, and I'll do some examples of this next time since we're out of time, but let me just describe them in words. Our favorite thing to do besides the regular measuring device is like measuring in the plus or minus basis. Okay? You can get a lot of mojo and like interesting quantum effects by playing around with like having a photon or a quantum particle and measuring it in the standard basis. That's the usual measuring device that resolves to 0, 1, and also the plus or minus basis. And in fact, I'll show you next time, and I guess I'll bring back the 3D glasses, a thing you can do. You can think about why this is the case. I'll just end by saying it in words. You take the laser pointer and put it through the horizontal filter and then also the vertical filter, the turned one, then no light will get through. But if you take a third filter and put it in between at a 45-degree angle, light will start to get through. And that's weird, right? If you just think about it from like a childlike intuition, like you have a horizontal filter, a vertical filter, no light gets through. Now I'm going to like put a further impediment in between, like that should surely only block the light more, right? But in fact, now suddenly light gets through. And this middle device is like measuring the photon in the plus or minus basis. And so you can think about why that happens. And I'll tell you why it happens on Thursday, and you can try it yourself.